So today we want to look at gravitational radiation power. However, before we do that, we just want to make sure, first of all, that we work out some of the... Now, if you look at this, given the conditions where the E is there, the polarization tensors, these are conditions that we obtained back then when we were talking about the TT gauge. And so given this condition, for which, especially if Ki is in three direction, the polarization tensor is supposed to have just two components. We want to work out these two components exactly so that we'll see what they look like in terms of the energy momentum tensors, which of course is what we expanded. So this was actually something that we tried to obtain last time. Actually, we did obtain that. We wrote this to be written in terms of that. And we want to note also that when K, or when we're in the three directions such as this K3, that the not component or the time component is equal to just the 3 component, if you like, that way, that fashion that I've written them. So having noted that, of course, one other very important expression that we obtained was that. That is what it is. It just means, of course, that the vector is neither in the one direction or two directions. So if we are looking at 1, 2, 3 as different propagation directions, and we single out the three direction, then of course we can see from this expression, if you substitute K3, and you will divide that by omega squared, of course, with that we could just have that as K hat and K hat and Ki hat and Kj hat, if we recall, because we said that Ki all over omega is equal to Ki hat. The square of that, of course, is 1 because that is a unit vector. So moving on, first of all, in the polarization tensor, for the plus polarization, we said is equal to either E11 or minus that. And by that E plus so I can say E plus being equal to E11 to be equal to here, 4G, so using this expression, all over modulus of G. And then I'm going to have here, so for the moment, for ease of manipulations or calculation, I'll dispense with this, but of course we can keep in mind that when I write something in the meantime, that this simply means is a function of both the wave vector and the angular frequency. So at this moment, I'll write this to be equal to this 1 minus 1 all over 2 eta 1 1 and T sigma here. I just said I don't need that. And this is what we get. Of course, so just by outright substitution. At this moment, we can see, first of all, that this, for instance, is a diagonal term, but it's equal to 1, because what we are going to be using subsequently is that this is 1, and that this I is equal to minus 1 for I, of course, equal to 1, 2, and 3. So at this point in time, this is 1, and also it will be good for us to see that T sigma, so if I can write this as eta, for instance, rho sigma, T, rho sigma. In our characteristic way of expanding, we will want to first of all sum through rho 0, 1, 2, and 3. In the end, then for each of those terms, we also sum through sigma. But having known already that eta rho sigma is equal to 0, of course, for all rho not equal to sigma. So is the diagonal metric. So because of that, we can just simply go straight in saying that T sigma is equal to eta naught T naught plus eta here 1 1 T 1 1 plus eta T 2 2 and plus eta 3 3 T 3 3. Where both this, all this 1 2 3 are equal to 1, but this alone is equal to minus 1. So in the end, you can see that this is T naught minus. Okay, sorry. I think I should try to reverse this in the way that, sorry, in the moment I need to get this. I can say that this is T, 1 1 plus T 2 2 plus T 3 3 minus T naught. That is what this trace, the trace of the energy momentum tensor is. And then, of course, at this moment, you can see that we have a minus half multiplying all that. So I think having explained with this, it's enough to just go straight ahead. That was equal to 1. So this will then be equal to T11 plus T22 plus T33 minus T naught naught. And we've just stated, of course, that this is the same as that. So right from the beginning, this of course is gone, these two, because that's what we noted right from the beginning. And since the two are the same. And then of course, here we have T11 minus half T. So what I will have in the end is, so I'm going to have 4G all over modulus of X, then 1 all over 2, which will be common in the end, because T11 minus half T11 is just half T11, but I've pulled out the 1 over 2. Then of course I will be left here with minus, again, half T22. So you can see that both have in common. So that by the end of the day, what we're going to have in essence is that, let me get this all cleared out. What we're going to get in essence is that our E plus is equal to E11 or minus E22, and in the end is the same thing as 2G all over modulus of X here times T11 minus T22. And of course, where T11 and T22 are both functions of K, omega, as we have indicated there. So this is the plus polarization written in terms of the energy momentum tensor. The cross polarization, I believe, should be simpler, because this will then be equal to, for instance, just like has been stated here, either 1, 2 or E2, 1. So just like we have we did with the first case, what we have to do here is to say this will be 4G all over modulus of X. And then what I'm going to have here is T12 minus half again, but eta 1, 2, and T sigma, sigma. We are spared with the calculation of the second term because given that this is a diagonal metric, of course, as you can see, this part is going to be 0 because that is 0. And so all we are left with is simply 4G all over modulus of X, T12. And that is the cross polarization. The plus polarization is equal to TG all over this times that. The cross polarization is equal to this, is this equal to that. And so that's what we have done here. And the next thing, of course, as we have stated right from the beginning, is we want to proceed in calculating gravitational radiation power. First, we want to mention a few terms that, and also define some formulae that will be important for this evaluation. The energy momentum in gravitational waves can be obtained from this expression. This expression is 1 over 2G. So for instance, I think I would like to use this equation here that I've written down already to explain this. This is the Einstein field equation, written as here what we know as the Einstein or the Einstein tensor to be equal to that. Now, if you look at this, what I have here is second order, meaning of second order in the perturbation metric, h mu nu. The calculations we have done so far in our linearizations, which we did quite in some detail, the linearization in terms of the h mu nu has so far been in first order of this perturbation metric. But now, proceeding, we need to calculate the energy momentum tensor. In fact, this is a pseudo tensor, but like we're saying, this is here second order and second order. So you can either calculate T mu nu directly as that, or you can decide to say that T mu nu is the same thing as, of course, the same coefficient here, 1 over 8 pi, as this one here minus the first order. So the idea is you can expand this Ricci tensor or scalar in terms of the, in order of which, or in order in terms of the order of the perturbation metric. So for instance, I could expand this in terms of first order plus the next one in terms of second order plus third order and so on and so forth. I could do that. So if you look at it carefully at this term, what it means is, for instance, if I expanded this expression to the second order, I will have one term which I can call maybe my first term in the first order of the perturbation metric, plus the second term which would be in second order of the perturbation metric. If I take that term and move to the other side of the equation, what I'm going to get is something like this. Can you see that? Let this T mu k, for instance, so well, I've been written as T mu nu, but it doesn't matter, but just in case we're consistent with the argument, I can just use k all over the place here. K. So again, let me take that again. I could write this, for instance, in terms of first order in perturbation metric plus second order in perturbation metric. Actually, we could go on in third order, fourth order, and so on. But if we consider what is negligible to be only from the third order in perturbation metric, then we can keep the first and second order. Now that second order is what will move to the right hand side of the Einstein field equation, and this is what it will be, and of course this is what it is. So it is either that second order term is equal to that, or it's also the same thing as saying, well, what is left on the right hand side will be the whole Einstein field equation itself being expanded in all orders of the metric perturbation, but for which we understand that every term higher than the second order metric perturbation is negligible. So in real sense, what is actually contained here is just the first order in perturbation metric and second order in perturbation metric. Now when we subtract out the first order perturbation metric, we are left with just second order perturbation metrics. In other words, this expression here is just equivalent to that here. Okay, and like I've said, this is just the pseudo tensor, and for the component of which we raise the indices I naught, this will be the energy flux vector. We're just doing this correspondingly with what we will have, where this to be the energy momentum tensor. So, and Team UK here is the energy momentum of the gravitational field. That's what this is the this here, this expression, so not this, either this or this one here, as I've written here, is the energy momentum tensor of the gravitational field. Now, one thing you will notice about this equation is that, well, it's going to act as a source term here on the right-hand side. Not only that, it's also going to be dependent on the perturbation metric, as we can see from here, or from here. And of course, this can be seen, for instance, or taken to mean that the perturbation metric is being generated by the total densities and the energy momentum and the energy and momentum of the field itself. So at this point in time, from here moving on, we are going to say, for instance, that one other concept, for instance, that I'm going to define. By the way, when you are taking the mean or the average of this expression, what you are meant to obtain is this. This is one thing I'm not going to do, well, not because it's not that important, but I think given the number of works we have done, exercises we've done so far in terms of linearized gravitational wave theory, this should be a simple exercise. However, if you find a problem with this, you can find a guidance to this derivation in Weinberg's book again, Gravitation and Cosmological Principle, chapter 10 in particular. If you need more elementary introduction and more detail in terms of what all this means, you might as well also check the chapter 7 of the same book. But what I'm interested in, as you can see right from the beginning in this presentation, is the gravitational radiation power. So which is why I'm going into, in the moment, unless I deem this absolutely necessary in the future, I wouldn't do this. So, but I think it's something any good student who is interested in learning any of this will want to try their hands on. So at this moment in time, what we have next is the following expression. And what we are calling this equation is the energy per unit time radiated in a solid angle, the omega, in the direction of x hat. Of course, you can see that this represents a differential, a dp, and what we mean by the power. And if I divide this through, or divide through by this d omega, or the solid angle, what I will obtain then is the radiated power per solid angle. And this, of course, is what we want to go to and see through the expression or calculation to the end as to what we refer to the gravitational radiation power in the end. And hopefully in a few moments we'll be able to see how to get there. So quite simply, you can see from this expression or from this, you can obtain this, is what I've explained. And then again, of course, you can write this like in this form, Ti naught, take the average, this is what you obtain. And then, of course, you can see already that if you can interpret this or that from here, the next thing you can get is this expression here, because you will then have to substitute this into this expression. I think that is already simple and easy to see, because all you have to do then is, for instance, if we are rewriting this expression for T mu nu on top, then for mu and nu, both, okay, well, you can say, well, let me take, for instance, if, okay, so as it is, so by the way, so like I've said, this is the energy per unit time radiated in a solid angle d omega in the direction x hat. And of course, when you've walked through all that, like I said, all very simple and something straightforward, we come along, or we arrive at this expression. And of course, at this point in time, what it then means is we can, for instance, rewrite this expression, and this expression we are calling the radiation power per solid angle. We want to show, for instance, especially using this expression here for the polarization tensor, we want to show, using this expression here in this formula, that this expression can be written as that. And that's the next thing that I do in this right now. So, of course, just as we have stated already, we have this expression which gives us the radiated power per solid angle. So, like I've just stated, we want to show that this expression, by the way, could be written as that. And the number one step, of course, is if we recall that the polarization tensor is given by this expression in terms of the energy momentum tensor. And this, of course, was the trace T sigma sigma, and which we could write as that, eta rho sigma or T rho sigma. So if that is the trace, which is T sigma sigma, which we could write as this or that, then we can, of course, if we recall, we just made use of such an expression. What we obtain in the end as the trace of the energy momentum tensor is Tii minus T naught naught, where I, of course, as usual, is from 1, 2 to 3. So all I'll have to do, the next step, is to substitute this into this place. And of course, I've done this in 2 steps because the next thing I did was now to raise one of the indices, the first actually, which is mu. Of course, in doing this, if I'm using some metric tensor, what I'll get is probably some rho all along, but again, since it's a free index, if I change it on the left hand side, I just have to make sure I perform the same change on the right hand side. So they might as well all be mu all over again. And then in the next step, what I'll have to do is to contract by contracting mu and nu. So this mu will be equal to nu, and then mu again, mu and nu. And of course, if mu is equal to nu in this case, then we have 4, and that is what it is. If I divide that 4 by 2, and then again express this T mu, just like I did for T sigma sigma over there, if I express this as that, and minus 2 times that, I end up with minus 4g all over modulus of x times the trace of the energy momentum tensor. So in other words, that T sigma sigma will end up being some T naught naught minus Tii. Then you pull out a minus, and this is what you get. Okay, now, so moving on next, again, is I try to write the polarization tensor in that expression as a covariant object. So as you can see, the mu nu have been moved up. And that is the only change that we have here in this expression. Is the only difference between this expression and that one over here. Now multiplying the two by taking the conjugate of this and multiplying it with that one, which has the covariant indices. And that's of course what we have done. Again, as usual, I'm dispensing with the k comma omega that is supposed to be before the energy momentum tensor. So what I do first is to take the conjugate of this expression and multiply it to the other one after the other as I perform this expansion. Of course, I will have this conjugate multiplied by that, and this conjugate, of course, multiplied by eta, half of that, and then T sigma sigma. By the end of the day, what I have in that expression will be something like this. This T mu nu conjugate multiplied by eta mu nu is the same thing as just the trace of T, or the energy momentum tensor. Of course, the same thing is what I will have here. But then again, this expression here is the same thing, or is equal to 4. So by the end of the day, this is just another trace, so I might as well write this both as T, and this also as T. So, but then of course, this is taking a conjugate, and then again, this is also just another T, but then it's conjugate. Of course, what you're going to have in the end is that this is going to give you 4. You have just one of that, and you have minus half T conjugate here, and then another minus half. That will give you minus T conjugate, then plus another T conjugate that you obtain from here, and that will be 0. So that in the end, the expression for this is simply equal to just 16g squared over modulus of s squared times that. And of course, as we have stated right from the beginning, which was the very first thing we did, we have obtained also the contraction of E mu nu to be equal to that right from this expression. So of course, it's these two expressions that we are going to substitute into this, which is what we have off of this expression, this factor that we have just called out from this expression of the radiated power per solid angle. So if I take this, for instance, for the first one, I'll substitute there, and then this expression, of course, here, I'm supposed to have minus half of the modulus squared of that. Now, if I do that, the next thing I'm supposed to obtain, of course, is this. This is what I get eventually. You can see that already here. I don't need to, this is a common factor, it goes out. I take the modulus of this, I get a 16 here, and another g squared, and of course you can see modulus of x squared also comes out. And the only thing that remains there, of course, which has been there right from the beginning, is the minus half, and so it's just the modulus of t sigma sigma there. And with that, then I simply substitute this expression. So you can see this factor of 16g squared over modulus squared multiplies with the factor here. So the 16 and 1g here is cancelled, leaving us with 1g on top. And then modulus of s squared that is on top here cancels the 1 down here. And then, of course, it disappears from the expression. And, of course, pi is left untouched because we have no pi from this expression. In the next step, of course, what we want to do is to see how further we can reduce this expression, especially in the spatial components. Again, as we talked about the TT gauge, we are interested here at the spatial, only on the spatial components of this expression. So, for instance, starting with this one here, what I'm trying to do is just to expand all this. Then, in the end, I'm going to use the expression that we obtained then in writing all the energy momentum tensor components in terms of the spatial components, in writing the time and time components just in terms of the spatial components. So the very first step, summing over this first term, you can see, of course, I'll start with summing over mu, and then I'll have not for the first one plus I, which again, by as usual, I is 1, 2, 3. And then nu I've left untouched. The minus half the modulus of the trace of the energy momentum tensor. Now here in the next step, I'm going to sum over nu again in this object. Now what I'm going to have is not for nu plus jj. I'm using j for the nu this time around. Then plus, here again I'm going to sum over nu. I'm going to have not with the i's again left untouched plus again jj this time around, where again both I and j are equal to 1. Okay. Now then, of course, I have minus the modulus of that squared, which this I might as well write as that. And then again, if I did that, this is what it will mean. If you recall, we've done this at least twice now. This we can write as that because, of course, that's the expansion. The square of this will mean one of this conjugate times the other one. And I just expanded that already, as you can see, all laid out. And this is what we obtained. Now, one thing we are going to try to address is, first of all, from these first expressions, not the trace, obviously, but as you can see in this one, I have first covariant indices, contravariant indices, and covariant indices. The same with this, and this. So all four. We want to find a way to write them all in terms of contravariant indices. So that in this case, for instance, okay, so these are all numerical values and not indices. So they shouldn't be alarming that I have up to 4 of this being repeated on one object. The same thing with that. So we just have to be very careful and identify and understand what it means. But as time goes on, we are going to see, of course, we are going to have to make these distinctions, because if we don't, we are going to run into some troubles. So, however, to range these two not or zero indices top, I will have to use eta not down like this and eta not down like this. Both are, of course, equal to -1. As you can see, because if I raise the first knot, I will require a eta not with the -1, and the next one just like it. And then, of course, that will eventually lead to me having this to just being equal to that. However, this next expression is different because I have just one knot, or should I say, yes, one time component. If I raise that 0 with this will eventually be -1. But when I raise this partial component j, with some j also, I'm just trying to maintain the j. Of course, I'm saying do not find this alarming that we're having up to 4 repeated indices instead of just the usual 2 that we should have. I'm going to do it without them anyway, because as you can see, this term is written to be equal to that, and it's just repeated twice. So in the end, this is equal to 1, but this is -1, so that by the end of the day, this is equal to minus that. So similarly, this is also equal to minus that, since one of the components there is partial and the other one is time. However, for the total spatial components in this case, raising them all with just something like eta not I or eta jj just produces 1 in both cases. So it just means that this object is just equal to that. So in other words, we are going to just use these conversions, and we are going to write this whole expression again, but with all the indices contravariant this time and none of them covariant. And so for the first sum of first year's expression, this is what we get. You can see they are all covariant. The minuses that we have inherited from this raising and lowering are here. And of course, what we've obtained from this expression here, what we have done here so far is simply to have taken the trace. Or how am I going to put it? Yeah, exactly, because we've got a minus sign here. And when we perform this expansion, I think I might have made a mistake. Please, so let me just correct that. T conjugate times T here should give me the first term. The next one there, please, should be a minus sign. This should be a minus sign. And then now I'm going to have again another minus. Okay, yes. Then plus that. So of course, eventually, one of the reasons why I have to write all this out to avoid unnecessary mistakes. So this is the minus here, and this is the minus here, plus of course the last time T naught not T. And that is what we've got. Now I'm going to erase this all over again just to continue further with it. Okay then, so as it is now, of course, this is the expression that we sought to write all completely in terms of the space components. So like we stated before, so I'm going to here just, yeah, of course, these have already been substituted, everything else I've written, and as you can see them, is all in that form. So what I'm going to do next is just to do some kind of collection of like terms. I have here to be all time components, and I have a minus half of something like that also in that bracket. I pull it out and then I combine the two together in one single term. So eventually, this will give me just half of this in the next step. And then again, I have minus this, and then minus that, as usual, plus the last one there. Then minus. So in the next step, what I'm going to do is to try to kind of rewrite this expression with some chronicle deltas. Of course, as you can see, this one, for instance, has 4 repeated indices. And like we said, this wouldn't be the right thing for us for any tensor expression. However, one other reason for doing this is to make sure that we can, in a way, be able to write them all in terms of a common factor of the products of two energy momentum tensors. For instance, this II and II here, I might as well rewrite as TLL and MM, but I know that these two are the same, so I must apply to the chronicle delta of ILM or iota M. Now, of course, what is here, by the way, is some II, so I can write that as or iota M, and then multiply that to the chronicle delta of the same thing. The same thing, of course, applies for this, but I use here Kn or kappa N, and this is still not known. This, of course, has been combined with this term here. So in the next step, looking at this one, especially because, like I said, this is coming from here. This expression here is given from me here, as you can see, is coming from this expression, whereby when we had, if you recall, T0I, I believe, is equal to some kind of, this will be equal to, of course, let me just take one here, Kn, Tn, J, because the J is repeated. This is an expression we have obtained before, and one of those, of course, is another one which, if you recall, is this T naught not being equal to that. So this is something we use, especially then when we talk about the TT gauge. So having written this in this form, exactly, so in other words, we have written this one and this one all in this form. So this one, the one with T naught J, has case of N, and the one with T naught I, anyway, well, it's just the same thing that we have just written here. T naught I both have I, and which is why both have the same JJ following them. And then, of course, here I have also multiplying iota here and iota J. So it just means that I can attach this to this and this to that, just like I've illustrated here. The same thing, of course, this one, by the way, is IJ. So it's already in spatial components. All we're going to have to do is to attach them with the chronicle deltas. So, okay, I guess I talked about this should be for the JJs and this should be for the II. Of course, the same thing is applicable for the two of them. In this case, of course, TI naught, I've represented either one of them, so you can choose one. So you can see II is common to both sides. So II again follows us. IM here is multiplied with KM, just a kind of version for this one, for which J will be replaced by I. And iota I is going to be attached with case of iota, which will take up, of course, this particular one. Just again, writing this with using a similar expression like that one. Now, this expression here, I have IJ. I know that I and I here is the same, also the same thing as JJ here. So what I do is I have I and iota, so I multiply with the chronicle delta of I iota. JJ, I multiply with the chronicle delta of NK or N kappa, whatever that is going to be, or whichever is suitable. So that's why I have N here and kappa here. And that's how I write that expression. Of course, the same thing is applicable or carries over to what we have here in the bracket. After doing that for the second term, yes, of course, we've done that already for this one. The same thing is applicable for these other terms here that are left. Of course, in this other term here, I already have here with me chronicle delta Kn, which again has come from this particular expression. As you can see, this is T naught naught conjugate, TII. Then I just add Kn here, and this is what I have. So the next step just involves further simplification. And what has changed so far is the fact, of course, that what I've got here is, this is minus that, nothing much has changed here. But this, of course, I have T naught naught. So what has actually changed there is that we have used an expression like this. As you can see, T naught naught being Ki Kj, T sub Ji all over omega squared. So T naught naught here has K rho K kappa, K rho K sigma, all has, these are unit vectors. But so instead of naught naught, it becomes rho sigma. So by using that expression, and then of course I still have here with me following what I know should have been the same thing on this chronicle delta iota, chronicle delta Lm. The minus this one, T naught naught again, I believe again, just as here was also written in terms of the special components. So please, the rho and sigma here means special components. In other words, they range from 1 to 3. So it doesn't look like the usual index used for the 1, 2, 3 indices. So I'm going to change that, rectify that. What we know or we normally see is I, J, and maybe even K and iota. These are what we know to be popularly used to denote a range of 1, 2 to 3. Now the next step, of course, you can see I have T naught naught conjugate and T naught naught here also. So the conjugate and this wouldn't change anything, but except of course for the fact that